Timothy Rinn, that will talk about how to unlock the physics of the Quark Gluon Plasma using the sPHENIX experiment at RHIC. So, Tim, whenever you're ready.
All right. Hopefully everyone can see slides and things are sharing correctly.
Perfectly.
All right, perfect. And thank you to everyone for coming back so quickly after the rather short coffee break. But as said, on behalf of the sPHENIX collaboration, I'm here to talk to you today about unlocking the physics of the Quark Gluon Plasma with the sPHENIX experiment at RHIC. So sPHENIX, as identified in the nuclear physics of the long-range plan of nuclear physics, has the stated goal to probe the inner workings of the QGP by resolving its properties at shorter and shorter length scales. And this is going to be accomplished with sPHENIX, as it's designed as a state-of-the-art jet detector, and it will be located at the relativistic heavy ion collider facility. And so sPHENIX has a four-prong core physics program, three of which I will be focusing on here today are focusing on the Quark Gluon Plasma in heavy ion collisions, but there's also a significant cold QCD program that is planned, and I have many colleagues who are very interested in that. But so as far as the probes of the Quark Gluon Plasma, I'd like to highlight these three main programs. The first is studying jets. As I mentioned, sPHENIX is going to be a state-of-the-art jet detector at RHIC. And what we can study with sPHENIX, given the fine spatial position resolution and the good energy resolutions, we can study not just jets in terms of their nuclear modification factor at a fixed radius, but we can actually study jets and their correlations with, for example, the event plane, as well as the substructure of jets. And this will allow us to vary the angular and momentum scale of the probe of the QGP. Additionally, we plan to have an open heavy flavor study, which will allow us to vary the mass and momentum of the probe of the medium. So we can study the mass dependence to interactions with the QGP by studying the quenching or the interactions of the various mass probes. Additionally, we can look at the QGP with a variety of sized probes by varying, looking at the upsilon 1, 2, and 3s states. And so these are the three kind of main QGP targeting observable programs. And of course, these are all discussed in the original sPHENIX proposal, which I have a link to down here. Now, in order to pursue this, the sPHENIX collaboration is a large global effort. We currently have over 300 members from at least 83 institutions from 14 different countries around the world. So this is really a large group of people from a variety of backgrounds coming together to make this a reality. Now, a little bit about the detector. So the sPHENIX detector is located at covering the mid-rapidity, primarily focusing on the region between plus or minus 1.1 in pseudo rapidity. And it has a powerful tracking system. It's a three-component tracking system. First, and closest to the collision vertex, we have a MAPS-based vertex tracker, or referred to as the MVTX, an intermediate silicon tracker, or the INTT, and a time projection changer, or TPC. These combine with the powerful superconducting magnet to allow for the reconstruction and measurement of charged particle tracks. And a little bit more on these tracking detector systems. We have, as I mentioned, starting at near the collision vertex, we have the MAPS-based vertex tracker, which is made up of 3 layers of monolithic active pixel sensors, or MAPS, which is based on what is used for release. And these have benefits of having a very short integration time, as well as great spatial resolution, less than 6 micrometers. And this will enable a very precise determination of the event vertex, as well as projection of tracks down to the collision vertex in order to extract, for example, a distance of closest approach type measurement in identification of heavy flavor. Additionally, another key benefit of the MAPS technology is that these are actually very thin, only about 0.3% of a radiation length. So it's a very slow conversion rate. As we make our way out then in the detector, we hit the INTT, or the intermediate silicon tracker. This is made up of 2 layers of stripped silicon sensors, similar to what was used for the pHENIX stripped pixel layers. And these will provide both intermediate tracking between the MVTX and the time projection chamber, but also will provide pattern recognition and timing information. And then we reach, as we go out in the radius, to the outer tracker, which is the time projection chamber. And this fault is a compact design TPC covering a distance between 20 and 78 centimeters, and will provide has very good spatial resolution, and therefore, in combination with the magnetic field, can of course provide accurate momentum measurements of our charged particle tracks. Now, going back to the detector overview, in addition to the tracking detectors and a magnet, we of course have a calorimetry system, and we have here a 2 or 3-part calorimetry system with an electromagnetic calorimeter plus an inner and outer H-cal, or hadronic calorimeter system. And these will operate, the detector as a whole will operate at a very high rate in terms of the triggering system, as well as a high rate DAC with a 15 kilohertz trigger expected and more than 10 gigabytes per second readout through the DAC. And a little bit more on the calorimetry system here. So as I mentioned, we have a full electromagnetic and hadronic calorimeter with very large acceptance, reaching out to plus or minus 1.1 in pseudo rapidity, and full 2 pi azimuthal coverage. And we're using silicon photomultipliers for the light collection and readout in these modules. And now starting from the inner radius and working our way out, so starting with the electromagnetic calorimeter here, these are tungsten powder embedded into a matrix of scintillating fibers calorimeter modules. And these will have a tower size at the end of the day of 0.025 by 0.025 in phi and eta, and they take advantage of the tungsten absorber material that we can have a compact design with a large radiation length of material. So it's only about 14 centimeters deep, but consists of about 20 radiation lengths. Now, as we make our way out, then in the radius, we hit first the inner hadronic calorimeter, followed by the outer H-cal. And the inner hadronic calorimeter uses aluminum absorber plates with scintillating tiles, while the outer hadronic calorimeter takes advantage of using steel absorber plates, again, with scintillating tiles and embedded wavelength shifting fibers for the light collection and readout. And these, again, have a fairly fine positional resolution of 0.1 by 0.1 in eta phi. Now, sPHENIX, we have an extensive run planned, and we have, in particular, we have a planned 3-year running between 2023, so less than 2 years away, through 2025, where we will study a variety of collision systems, including gold-gold, proton-proton, and proton-gold systems. And additionally, there's a proposed expanded run plan if EIC construction allows, and that would include a variety of more exotic nuclei or smaller systems such as oxygen-oxygen and argon-argon, as well as expanded proton-proton and gold-gold data sets, and running through 2027. And so this will allow us to study the effects of the Quark Gluon Plasma in a variety of collision systems and a variety of sizes, while also collecting a very large amount of statistics, in particular in proton-proton and gold-gold collisions. And I'd like to highlight some of our projections in gold-gold, or projections for measurements in gold-gold collisions. Now, these are all going to be talking about integrated over the first 3 years of running. So that is 2 samples of gold-gold plus 1 sample of proton-proton collisions. And here, for example, we're talking about now the statistical confidence or statistical uncertainties that we expect to have on measurements of direct photons, hadrons, and jets. And we expect to be able to measure direct photons, as shown here in blue, up until about 35, 40 GeV with quite good statistical uncertainty, and which will greatly improve previous measurements of the nuclear modification factor, or the lack of nuclear modification observed by direct photons. Similarly, we expect to be able to greatly expand with a very large data set on jets, our kinematic reach, reaching from about 15 GeV up to about 70 GeV for the nuclear modification factor. And this will in particular enable a multidimensional jet studies from this new large statistical sample, and ability to look for both jet substructure as well as correlations such as jet photon imbalance. Now, additionally, we will have, of course, a large measurement of the inclusive hadron RAA, or large statistical sample for the inclusive hadrons, And this we expect to be able to measure the nuclear modification factor up until about 50 GeV. And thinking about the inclusive charge hadrons for a moment, I would like to talk very briefly about a recent publication from the Jetscape collaboration, which did a Bayesian analysis of world charge hadron RAA data in order to extract the jet transport coefficient Q hat, all within the Jetscape framework. And this took advantage of data from 2011 in Phoenix, so gold data from Phoenix, as well as measurements from Atlas at 2.76 TeV and CMS at 5.02 TeV in order to extract this. And if we look at the RHIC data, this is very nice data in of itself. However, if we think about in terms of the performance of sPHENIX and the sample that we expect to have, we'll actually be able to have enhanced precision compared to the Phoenix results that they compared to, and enhance the high PT reach of the measurement, which will hopefully provide additional constraint to these types of analyses in the future at RHIC energies. Now, talking about jets and in particular jet correlations, here are some projections of the photon jet momentum balance and the jet V2 measurements. And so the photon jet imbalance is actually a particularly interesting measurement, as by using a photon to tag your jet, as the photon is not modified by the medium, you can actually get a strong sense for the unquenched momentum that that jet had. And so by studying the modification of the photon jet balance in gold-gold collisions compared to proton-proton collisions, you can get direct insight on the nuclear modification or the energy loss of that away side jet. And shown here are projections of the statistical uncertainties that we expect to have in both proton-proton in black and in gold-gold in red. This is using Joule to motivate the shapes of the distributions. But we'll actually be able to do a very precise measurement in terms of our statistical capabilities. And additionally, we will have the ability to study the event plane dependence to jet quenching by studying the jet V2 with, again, high precision up until about 50 to 60 GeV in jet PT using these samples. And this will enable simultaneous comparisons of models across both the LHC and RHIC energies. Now, additionally, as I mentioned, another key goal is we want to be able to study the jet substructure. And this really takes advantage of the fine segmentation within the calorimeter and tracking resolution to really create both subjets and others, also to study, for example, jet fragmentation. And so shown here is a projection for the jet splitting function, or ZG, which basically shows the fraction of the momentum carried by the subleading subjet within a jet. And where we expect to be able to see strong evidence for modification of the momentum carried by the subjet compared to the primary or leading subjet in gold-gold collisions compared to proton-proton. Now, another avenue that sPHENIX is aiming to tackle is to study open heavy flavor. And so this will take advantage of the precision tracking and vertexing within the sPHENIX detector to develop this system. And so by studying heavy flavor quarks, as I mentioned before, we can gain insight on the mass dependence to interactions with the nuclear medium. And shown here are projections for the measurements of both prompt D0, so from charm, and B to D0, which would be then from your bottom decay, D0s from bottom decays. And what we can see here is that we have very good statistical power for the prompt D0s, but also significant statistical power for the measurement of the B to D0 decay channel. And where we can then really gain insight compared to previous measurements at RHIC in terms of the mass dependence to suppression between light and heavier quarks, such as your charm and your bottom, and particularly the mass hierarchy between the charm and the bottom. And similarly, by coupling with measurements of the event plane, we can measure the prompt and non-prompt D0 V2. And so we can then gain insight to the collective motion of the charm and bottom quarks with respect to the nuclear medium. Now, of course, we can couple the measurements of heavy flavor quarks with jets and study heavy flavored jets. And so using the MVTX and the other tracking detectors, we can enable tagging of heavy flavored jets. And this will enable the study of heavy flavor at higher PT, where the mass difference between the light and the heavier quarks is less significant. And we can add in information on the flavor dependence to the fragmentation mechanisms. And also, so we can see that in, for example, the RAA measurement shown here on the left. And additionally, the collectivity behavior in the V2 measurement, or projection, sorry, on the right. And again, here we expect to have statistical samples of with high precision up to 35 to maybe 45 GeV in kinematic reach with these data samples. Now, another measurement, the third prong that we had talked about for probing the QGP is using upsilon spectroscopy. Now, upsilon spectroscopy is interesting in the sense that it's very sensitive to the temperature of the medium. The high temperature of the nuclear medium that's formed, the Quark Gluon Plasma, results in a sequential melting of the upsilon states, with the higher mass states melting more readily at a fixed medium temperature. And the precise mass resolution of the sPHENIX tracking will enable separation of the upsilon 1, 2, and 3s states at RHIC. And shown here is a projection of the dielectron mass spectrum. And you see in the black points fitted by the red curve are the projections for gold, and using a 100 MeV mass resolution of the 1s. And shown in dotted and blue lines are projections from PP collisions normalized to the same integral of the 1s. And you can see the ability to distinguish between the various states. Now, shown here then are the projections of the nuclear modification factor, RAA, of these upsilon states, in particular for the 1 and 2s states. And these are shown on the left as a function of the number of participants, or in other words, or as thoughts of as a function of centrality, and on the right as a function of the PT of the upsilon. And what we expect to be able to see with very high precision is the sequential melting of these upsilon states, and particular both as a function of centrality and as a function of PT. Now, going back to sPHENIX, I want to talk about briefly the timeline, where we are and where we're going. So sPHENIX was proposed as an original upgrade and replacement of Phoenix way back in 2010. But since then, we have come a long way, with several test beam efforts having undergone both in 2016 and 2018, up through construction beginning and a whole significant number of QA up until where we are today, where the construction of detectors, infrastructure, and software are well underway. And we're approaching very rapidly the end of the planned construction around the end of this year, with 2022 having a significant amount of installation and commissioning and gold data starting in 2023. And so we're very excited about this. And just a couple of pretty pictures of the ongoing construction efforts. So for example, I'm showing here are photos from the time projection chamber construction. In the top left, for example, we have a picture of the inner field cage from when it was tested. This has now been fully constructed and tested at this point. And the gems are currently under construction, as well as the outer cage are currently under construction. With regards to the electromagnetic calorimeter, this again is currently under construction, with 50% of the calorimeter blocks actually having just been completed this past weekend. So we're well on track and making great progress there. This effort is ongoing both here in the States at UIUC, as well as overseas in Fudan, in Shanghai. And the sector assembly and testing is ongoing currently at Brookhaven National Lab. We additionally, for the hadronic calorimeter system, this is ongoing with significant tile testing ongoing at Georgia State University. And I'd like to highlight that they also very recently have fully finished the construction of the outer hadronic calorimeter sectors, and are now working primarily on the inner hadronic calorimeter. And so great progress is going all around, even in these difficult times. Now, I'd like to talk also briefly, as I mentioned, we've done several test beam efforts. And so what's shown here is a picture or a series of pictures of the setup at the Fermilab test beam site. from several years ago. But we've gotten actually a lot of interesting results out from this in order to verify both the detector performance. And so, for example, here we have a publication out on the electromagnetic calorimeter's performance, where it was seen that the resolution meets the design criteria of the sPHENIX calorimeter. And similarly for the hadronic calorimeter here on the right, and the time projection here on the top right. And with that, I'd like to reach my summary and outlook. sPHENIX will enable a wide range of precision measurements of the quark gluon plasma, and it'll be able to provide critical insights on interactions with this medium at RHIC energies, with first data expected just around the corner in 2023. And in that process, the detector construction is well underway, and final installation and commissioning is planned to start in December. So thank you very much.
Thank you very much, Tim, for this very nice overview and also for staying well in time. So questions from the audience to our speaker?
Daniel here, I have a question. I cannot raise my hand because I'm co-host.
Oh yeah, okay. Let's allow Ivan to ask first, and then you go.
Okay, thank you.
Thanks.
One question maybe on the last slide. How do you plan to calibrate your hadronic and electromagnetic calorimeter?
That is a very good question, and there's some work ongoing with regard to that. One of the ideas right now that we're exploring are using MIPS to develop a preliminary calibration and then to calibrate it using for example, the Pi0 mass peak for like an online calibration or offline calibration, sorry.
Okay, thank you.
Yep.
Right. Ivan, I see you have a raised hand.
Yes, can you hear me in the first place?
Yeah, yes, we can.
Okay, very good. So the talk was very clear. So, and you touched on this, but I just want like one sentence answer. Given that you're, you know, what, like two years away from the proposed data taking plan, you know, everything is on schedule and you guys are pretty confident that you'll be able to pull it out?
Yes, so as you can imagine with the COVID times, some of the construction efforts have been unique, let's say, but we are fairly well still on track for the planned turn-on date in 2 years.
Thank you very much. I think everything else very clear.
Thank you.
Actually, I have myself one question on the timeline. You often like show that you may go up to 2027 if EIC construction allows. So my question is it something like that is looking to a significant delay to the EIC construction, or it's something that you are negotiating and there is a room, for instance, to continue running while EIC is put in place? So can you elaborate a little bit more on
the construction of the EIC will at some point cannibalize the RHIC accelerator facility, as it's located in the same facility and using the RHIC accelerator as a component. And so it largely depends, from my understanding, and this could be mistaken, and if it is, I apologize, but the running beyond 2025 would require a delay from the current schedule of the EIC. So the expectation is that by 2026, RHIC will have to be shut down for the continuation of the construction.
I see. Thank you very much.
Thank you.
Any other question? If no, let's thank the speaker again. And okay, so thank you. Next speaker is Oleg Tsai, and he will give us a nice an overview of the forward upgrade for the star detector. Oleg, are you online?
Yeah, can you hear me?
Okay, yes, we can.
All right, so let me start sharing screen. How's my slide? You can see them?
Yes, we can. Perfect.
All right, so good morning, good afternoon, good evening, depending where you are. On behalf of STAR Collaboration, I give you an overview of a STAR forward upgrade, this new detection capability which we are using for STAR. To start this talk, so it's impossible not to say nice words about RHIC. So I think that it's fair to say that for past 21 years, RHIC was a real QCD workhorse. And it's arguably one most versatile accelerator, probably in terms of energy, species, and not to mention that it's only polarized collider right now. So as it was mentioned in last previous talk, so last long-range plan on nuclear physics recommend some measurements that had to be done with RHIC, and it strongly recommend to continue utilizing existing RHIC infrastructure to explore not just a hot cold QCD method, but also cold QCD method. So, and in particular, in the next few years, we will have a few runs with this respect. The first run will start a few months from now, actually. So it would be 500 GeV run with the transversely polarized proton. So the last run was in 2017. And in 2024, so once the sPHENIX will start to operate, so we would have, again, 200 GeV run in both PP and PA. Those was last run in 2015. And 2023 and 2025 is full energy gold running. Okay, so essentially in response to this recommendation in long-range plan, so RHIC spin community come up with so-called cold QCD plan, which was released in 2016. And this plan identified the measurement essential for so-called must-to-do measurements in PP and PA in physics preceding KAC. So those will focus on structure, hadronization, and interaction involving hadrons. These are measurements that will allow us to optimize and enhance the EAC program. For example, it will allow us to test factorizations and universality and TMD evolutions. So it's also was understood at that time that the last cold QCD run was in 2017 and EAC projected to start in 2031. It's a big gap. So and have solid plan for somewhere in between would be very essential to keep all the cold QCD community engaged as we move toward the EAC. So, of course, there is also hot QCD topics which STAR want to address during this running period, running in parallel with sPHENIX. And those questions arising from setting some constraints on longitudinal structure of initial state in heavy ion collisions, and put constraints on temperature-dependent transport of matter, and also continue the measurements with global lambda periodization in forward direction. So the measurement that STAR did a few years ago and published Nature paper. STAR experiment take a different approach than sPHENIX in terms of detector upgrade. So essentially STAR is continuously upgrading detector from the day one. So when we started just with TPC and central trigger barrel, and through the years we were adding more and more systems. So in particular, so if you look in terms of two particle correlation, so how the acceptance changed in past few years before we start BeAGLE Scan 2 program, it's clearly shown here. So we had, it was important upgrade of ITPC, and also we had EPD. So, and now the forward tracking system goes in place as well. Large and uniform acceptance is always nice things to have. So because it's, for example, in two particle correlations, it gives you control on short and intermediate range correlation. And if you can measure, according to at least a Hydra simulation, so if you can measure elliptic flow at forward rapidities quite accurately, you actually can distinguish some model dependencies of how the shear viscosity over S depends versus temperature at RHIC. So this is a program that STAR envisioned. So for the next 4 years, so we'll have 2 full energy run at gold in 2023, 2025, those in parallel with sPHENIX. And in run 22, which start a few months from now, we will run 500 GeV polarized protons. And in 24, we will have 200 GeV protons and PA. So the physics topics include TMDs, so measurements at high X, which will allow to constrain the tensor charge. Sievers through Brilliant, so this program that started back in 2017. And again, so added capabilities of Star Forward will add, so that now we can detect direct photon and work with stacked jets. In PA, so the questions that Star will address is Gluon PDFs, RPA, and test of saturation prediction. So all of these measurements are critical to the scientific success of EIC to test universality and factorization. So in terms of observables, so we're talking about diet jets, hadrons in jets, lambdas, correlation at mid and forward rapidities, which Star nicely can do right now. So this requires both extensive colorimetry in forward direction, both electromagnetic and HCALs, as well as tracking. So from tracking, so essentially for cold QCD plan, we're just looking at charge separation. And in terms of colorimeters, HCAL requires reasonably good energy resolution, but not a record breaking. What do we want to do with polarized PP? So just give you some measurements. So long-standing observations that single Kina symmetries are nearly independent from square root S. And it's still not clear what is the driving mechanism behind those. Star will continue these measurements, and now with the capabilities. So for just for neutral pi zeros, which we measured this previous detector, which was sitting at Star forward meson spectrometer. Now we can measure the asymmetries for charged hadrons. And it actually would be interesting to see whether or not so we would see the same, the sizable asymmetries when you go to the highest RHIC energy. And it's combining with the previous data. So the thinking is that this would be probably the best data set to constrain the evolution and flavor dependence of TWIS3 and UTQS distributions. Sievers through tagged jets. So those measurements are interesting, and they actually were spurred by observation of Andy that the jets essentially have very small asymmetries. So the theory made the predictions, and of course, so with forward upgrade, we will be able to reconstruct jets in forward direction, but we also will be able to have so-called biased jets. Let's say when we identify the leading hadrons within the jets. Going forward and having large acceptance, which Star will have during this running, gives you additional opportunities. In particular, if you look at the bottom row, so what is shown here is that Star essentially will push sensitivity to higher X and lower X at high Q square, reconstructing jets and charge hadrons in the forward direction. So which is shown over here. This region is very interesting because there is no experimental data in this region. And finally, let me touch on saturation. So this is where Star has a very unique, absolutely unique opportunity to have very high gluon densities in proton gold collisions. So just remind you, so the data set that have been taken previously, it was 2015 when we ran PP and P gold. And Star just show preliminary results. When you look at the dihadron correlation, so the wayside is gets suppressed, and suppression is actually what is observed in Star is actually follows this formalism, is consistent with color glass condensate formalism. So it was expected that it would be highest suppression for low PT hadrons when we have highest activity in the backward direction on BBC in this case. So additional capabilities, of course, would add additional probes in this. So we can do it with charged dihadrons, gamma jet, and dijets. So those, because expected delivered luminosity for around 24 would be something like 3 to 4 times larger than it was delivered in 2015. Again, so this is considered to be a critical measurements to test universality, because the EA program at TAC will be looking at the same things. So in terms of detector, we're talking about essentially 5 different subsystems. So next to interaction points, we have 3 stations of silicon disk, followed by 4 stations of strip thin-gap chambers. After that, we have EPD, which was actually in operation for past 3 years. It will be using like charge Vita in combination with ECAL and FCC-eh. So EPD, ECAL, and HCAL, so those are trigger detectors. So when the code QCD plan was realized in 2016, it was big uncertainties whether or not this upgrade may happen. So it was uncertainties whether or not we will have 500 GeV around. And actually, so STAR started to talk about forward upgrade almost 10 years ago, about the same time as Phoenix started to talk about sPHENIX. And in 2014, we actually tested high resolution colorimeter system in forward direction, for which we developed this new technology with tungsten Sci-Fi ECAL, followed by LED scintillating HCAL. Unfortunately, so this modest upgrade, which we kind of guided to think about, is not compatible with high resolution detectors. So the high resolution colorimeters cost a lot. So we had to reconsider our strategy, how we want to execute this forward upgrade, in particular, what type of technology we can use and can we afford them. So, and essentially, so because of all these uncertainties, which drag this program from realization, so we ended up reusing as much as possible equipment from past experiments. For example, for ECAL, we reuse all of the Phoenix Shashlik colorimeters, 1500 channels. We just outfitted with a new readout based on SciPMs. HCAL, of course, it's a completely new detector. So it was a version when we had a full silicon version of the tracker, but again, because of the cost, so we had to compromise a little bit. So, and put much more cost-effective thin strip gap chambers, this technology. Essentially, by the time when it became clear that it's possible, and this happened late in 2019, so we had in hands very robust plan where we minimize all technical cost and surgery risk by using and reusing existing equipment. So then in 2019, so we had a successful review, director's review at BNL. A few months later, we applied for MRI proposal for colorimeters. It was accepted. And in the fall of 2020, we start to place orders for those detectors. Okay, so what is the status of silicon tracker? I don't want to go through all of these details. So it was reported half a month ago during the STAR collaboration meeting. So it's in the final stages of assembly. So this is what you see. People are testing the wages. They're testing the cooling system. So everything works just fine. Again, so to make this project doable, so we're using a lot of equipment from a very successful project, which STAR ran during the heavy flavor program. It was intermediate silicon tracker. Essentially, the whole data acquisition system, cooling system, conventional system, it's all intact, were preserved from this time, and they all will be used for silicon tracker. So going forward with strip sync gap chambers. So this is technology. It's very old technology. So it's known for many years. The large scale implementation of this technology was at Atlas, essentially the same groups which have been building very large chambers for Atlas, now building those for STAR. It's again in the final stages of production, so and it's completely on track to be installed at the end of the summer into the STAR detector. So for colorimeters, as I mentioned, so ECAL was repurposed from Phoenix, and the strategy of STAR was to push the to have all the colorimeters built, installed, and make operational in previous shutdown, so that for the next summer we don't have too crowded space over there with 2 additional detectors coming in, and that was accomplished in this difficult COVID year. And you see over here in pictures how collaborators from our students actually putting the electronics on ECAL, on HCAL, and this actually assembly of HCAL happened in November, December last year. So it was turns out to be very efficient method to build the colorimeters at the end. So, and of course, it's a very large group of STAR collaborators who are actively engaged in all aspects of this project. So, as I said, the construction was completed. So this is just a fun pictures with LED test of a system when we check mapping, channels, alive data, etc. And there is it was also a news release at PNL. So FCS currently we are taking data with FCS because it's an ongoing run at STAR, the last beam and G-scan run. So detector is fully integrated in STAR. So, and this is essentially online plots from this run. In about months from now, we would have 1 week of oxygen running, and the goal is to completely commission trigger of the based on the colorimeters, the ones that will be running in PP500. Okay, so of course, to pull such an upgrade requires dedicated manpower with large expertise in each subsystem, and this is where STAR is shining. And maybe one of the reasons of why we were able to pull this upgrade in such difficult time and short period of time, because STAR essentially doing upgrade of the detector from the day 1. Essentially, so the STAR collaborators are, in this sense, are very well trained how to do such things. And I want to mention importance of this forward upgrade for future EAC. So early on, we understood that the forward colorimetry system and forward rapidity it would be very similar to what we will have at EAC. And actually, both technologies that we developed for STAR, so in terms of Tank and Sci-Fi and how to build HCAL, including carried out with Sapiens, etc. So those will go hand in hand with generic EAC R&D program. So and that was very helpful. So we learned a lot, but also it was a good feedback back to EAC. So in particular, so what will happen in Hadron and CAP. And of course, operating this system in conditions which would be at high luminosity EAC, it also would be very beneficial. So not to mention that projects like this, it's a good training facility for young scientists. And for example, when we had the ability to bring students to BNL, so in summer 2019, we had 20+ undergrads working with us. So this slide I shamefully borrowed from Elke because I like it. So indeed, this STAR forward and mid rapidity, of course, PPPA program, it is addressing fundamental questions in QCD. So it is essential for mission of RHIC physics program, and it is a real bridge. So on bridge, it's not just a program, but it's also keep community agile and ready to transform to EAC, and it's also technological connection between all the detectors that we are building right now and the detector which we will build for EAC in near future. So with that, let me conclude. So we at STAR believe that STAR is a really beautiful detector. So very soon it will be even better. So the enthusiastic STAR collaboration is working hard to complete this upgrade. So everything is on track. Calorimeter is already taking data. So, and it would be a really important addition to realize both cold and hot QCD program for STAR in the next few years. Okay, thank you.
Thank you very much, Oleg. So questions from the audience for Oleg? Ivan?
Hi, Oleg. Thanks for the talk. I was wondering if you go, I think, to it was slide number 9, when you were talking about recent STAR measurements of correlation broadening. Maybe it was this slide. I was wondering how this compares to earlier, I think, Phoenix measurements. I think it was about, already it must be about 10 years ago. I mean, are those consistent, or do you see essentially larger effects? Have you done any comparison?
Well, so I'm not sure about the Phoenix measurement. So I know that in DGOLD run, it was measurement from stars that have been kind of preliminary results have been shown for STAR for a few years. So my feeling is that those are consistent. So the argument that people are saying that it's better to do in PGOLD rather than DGOLD because PGOLD considered to be more cleaner system to study those things.
No, that's understood. Okay, thanks. And the reason for which I was asking the question is because, right, you can have a saturation description, but you also can have a multiple scattering description of those earlier data, and they worked equally well. And so, I mean, kind of, so to say, you know, you send the 1 GeV, 2 GeV particle to anything, it will multiple scatter and broaden. So perhaps the more differential observables, more differentiating observables are necessary for the IC. And I think people are realizing that.
Yeah. Okay.
All right. Do you have any other question for Oleg? Even again, you want to ask something else, or no?
No, I was just trying to lower it.
Right. So it's indeed impressive that STAR is pulling this, I think, on this tight time scale with these times that we are living right now. Okay, so thank you again, Oleg, for this very nice overview. And next is Ivan Vitev, that talks about nuclear matter effects in jet production at electron-ion colliders. Ivan, whenever you're ready.
So sorry, let me unmute. So let me make sure that you first see the screen.
Yes, we do.
Okay, very good. So I'll talk about nuclear matter effects on jet production at electron-ion colliders. And of course, oops, let me see how this one works. Okay, and certainly, you know, it's a pleasure to attend this, even though virtual, the IS 2021 event. So here is the plan for the talk, and here are a couple of useful references. The work is done with Haitao Li, and also Zhelong Liu was involved in some part of this calculation related to the mesons. The work is supported by the TMD Topical Collaboration for Nuclear Theory and the LANO LDRD program. So the main topic of this talk is actually to explore what's going to happen at electron-ion colliders in electron-nucleus collisions as opposed to electron-proton collisions. So the main questions that we're interested in are illustrated in this cartoon, which shows a virtual photon striking a quark, and then the quark propagating in the large nucleus, interacting and developing an in-medium parton shower. So what we need to understand are those parton showers, because they're at the crux of all higher order and recent calculations. And the main ingredient of parton showers are the splitting functions. The ones in the vacuum we know very well. They're Autorelli-Parisi splitting functions, and there are different ways to calculate them. But one technique that's quite useful and often used in saturation calculations is the light cone wave functions. We can write down the wave function for the splitting into the final state, and then by squaring it and putting the relevant phase space, we can obtain all of the Autorelli-Parisi splitting functions. And there is an advantage to using this light cone technique because it gives in one shot both massive and massless splitting functions. Now, this calculation is quite technically demanding, but it has been done several different ways. So we are quite certain about the result. First, it was done using effective theories of QCD, such as soft collinear effective theory, and then it was checked specifically with deep inelastic scattering in mind with this light cone wave function approach. So here is how a typical splitting kernel, differential in both the momentum fraction x of the splitting and also the transverse momentum of the splitting, will look like. It is proportional to the Autorelli-Parisi splitting function in the vacuum, but then it also depends on the properties of the medium, such as the scattering length, the distribution of the momentum transfers from the medium, and it takes into account kind of the relation between the time and length scales in nuclear collisions, the so-called Landau-Pomeranchuk-Migdal effect. As a result, the in-medium parton showers are softer and broader in comparison to the vacuum. And this is the crux of, in addition to having them, this is the crux which will lead to observables in electron nucleus relative to electron-proton collisions. Of course, the splitting functions have nice theoretical properties that I list here that can be proven rigorously. Now, from the point of view of QCD factorization, this means that there will be additional contributions to the factorization formulas. For example, if we look at hadron production, there will be additional medium-induced scaling violations or evolution of the fragmentation functions. And this can be tested against existing data, for example, from heavy ion collisions. The pink band shows here this SCAT-G in medium evolution approach, and in fact, it gives better prediction of the suppression of hadron production here seen by CMS in comparison to traditional energy loss approaches also shown. Now, with this in mind, we can move and address hadron and jet production in electron nucleus collisions. And this is the cartoon. We have to take into account the final state parton shower induced in the nucleus. But in order to make educated predictions, we first have to constrain a little bit the transport properties of cold nuclear matter. And we do this using the Hermes measurements. As a reminder, Hermes was a fixed target experiment at Hera using the electron beam of 27.6 GeV. And what the experiment measured was this double ratio. For example, the differential distribution for pion production normalized by the corresponding inclusive electron scattering cross-section in the nucleus and compared it to deuterium. The reason for which a double ratio was done is to eliminate initial state nuclear PDF effects. So when we see a suppression or any modification for that matter, here shown as a function of the parton energy nu in the rest frame of the nucleus, or as a function of the hadronization fraction Z, you see very clear suppression. We know that it comes from final state interactions. It's not a nuclear PDF effect. And applying the technique of in-medium evolution, we can constrain the transport properties. So Q hat, typical momentum transfer square per unit length for quarks, is 0.05 Jeff square per Fermi. And for the gluons, it's of course 2.25 times larger. This is the ratio of the Casimirs or color charges square. With this in mind, we can go and do the same calculations, first for hadrons, because we want to understand what are the center of mass energies And what are the kinematic ranges in rapidity that are most suited to study this type of physics? The type of physics that I'm talking about is the physics of parton propagation and energy loss inside the nucleus, or alternatively, there are models of hadron formation at very short times and then hadron absorption. Now, for the purposes of EIC, we have larger center of mass energies, larger parton energies, so the first picture would be more relevant, and this is what we study first. Now, we've done calculations at many different center of mass energies, different rapidity intervals, and these are the two figures which kind of illustrate the contrast. If we look at high center of mass energies, these are the highest center of mass energies. In fact, I don't think they can be done with a nucleus. And we look at any species, the nuclear modification as a function of the transverse momentum relative to the collision axis in the backward electron going rapidity, we see that the modification is really very, very small. So this is not the region to look at. Now, if we want to study this type of physics, we have to go to small center of mass energies and forward rapidities. And this is very well illustrated here as a function of the fragmentation fraction z. For pions, especially at forward rapidity, 2 to 4 GeV, the suppression is just spectacular. It's more than a factor of 2 to a factor of 4 suppression as a function of z. It will be very easily measurable at DIC. Now, this talk is dedicated to light hadron and light jet production, but if we want to study the physics of hadronization, it's better to study heavy meson production. Unfortunately, this is a topic of a different talk. Now that we know what center of mass energies to look at and what regions in rapidity, that would be the forward proton or nucleus going region, we can go to the main topic, the jet production. And one of the ways, although not a unique way to calculate jet cross sections, is using the technique of semi-inclusive jet functions. This is the factorization formula, and what you will notice is that it is exactly the same as the formula for hadron production. Instead, the fragmentation function here is substituted with a semi-inclusive jet function. The inclusion of the jet function and also the fact that we reconstruct jets with a certain radius induces new scales, such as the so-called jet scale. It's the hard scale times the radius. And when the radius becomes small, then there is hierarchy of scales that we need to resum. And we can also do that using, for example, time-like JLab evolution equations. As I advocated earlier, the fact that we have in-medium showers means that there will be a medium-induced contribution to the factorization components, in this case to the jet function, and here are typical diagrams that will give the in-medium contribution to the jet function. Not surprisingly, the jet functions can be expressed in terms of the parton splitting functions in the medium, which we had calculated before and tabulated, so we are ready to calculate. And with those jet functions, we can do next to leading order calculations of jet production in case of nuclear matter. So here are the results, how jet production in EA collisions will compare to the one in EP collisions. We construct the nuclear modification ratio. Here, the normalization factor is 1 over the number of nucleons. This is the trivial multiplicity normalization factor, just like we have TAA in the case of heavy ion collisions. And we have two types of nuclear effects that will play a role on jet modification. First, we have initial state effects that perhaps can be parameterized in nuclear parton distribution functions. And then we have final state effects from the interactions of the jets in the medium. And here what we can try to do is use the jet radius parameter, and by varying the jet radius parameter, we'll leverage the difference in the shape and the distribution of in-medium parton showers as opposed to vacuum showers. I emphasized that they are different, and this is the essence of jet physics when we have a nucleus involved. The results are shown in this figure. You see first the individual contributions, the blue band, and the band includes uncertainties and variations of scales, gives the initial state nuclear PDF effects. You see small anti-shadowing, and then most of the suppression here is dominated by the EMC region, suppression in the EMC region. Now the green contribution is just from the final state effects. It starts at the level of about 20%, But as we go to high PT, it gradually disappears. And finally, the full result is the red band. And you see that the suppression, in fact, for even moderately large radius jets of 0.5 is, 20 to 30%. Those are large suppressions, and they'll be easily measurable at DIC. We went a step further to just kind of see what happens with different nuclear PDF parameterizations, and we used NCTEC 15 and TPPS 16, and you see that the two results are really extremely similar to each other. The difference is less than 5% in the absolute cross-section. So we were a little bit surprised by this, but it's also nice to see this level of consistency. Now, in order to study nuclear PDFs and parton showers and understand what their different contribution is, we have to separate them. And the way in which we propose to do that, in fact, we demonstrate that we can do that, is to take a double ratio. The modification of a jet for certain radius are, the smaller the radius, the better, divided by the modification of a jet of a large radius, for example, R equals 1. The reason is that the initial state effects are the same on the nucleus, and they'll cancel in the double ratio. So this is illustrated in the figure on the right-hand side. If you look first at the bottom panel, then in this higher center of mass energy, you will see that we've successfully eliminated initial state effects, and those bands look like, the contribution from final state effects only. But even more importantly, when we go to smaller center of mass energies, as we know from our hadron calculations, the effects become much more pronounced. There is very clear separation in terms of suppression as a function of the jet radius. And when we go to small radii on the order of 0.3, the suppression is almost a factor of 2. This is a spectacularly large suppression for cold nuclear matter. These are the types of suppressions that we have seen in the Quark Gluon Plasma. And so this is a very promising way to study jet energy loss and cold nuclear matter transport properties at the Electron-Ion collider. We have gone a step further just to verify that none of our conclusions depend on the choice of PDFs. We've done calculations with different MPDFs as a function of the radius. Again, the differences are less than 5%. And when we take a double ratio, you cannot distinguish in this figure on the right the dashed lines from the solid lines, which means that these are two different nuclear PDF parameterizations. The effect completely cancels away. So the last topic that I want to touch on is jet substructure at DIC and the jet charge. And so a fundamental prediction of the theory of jet modification in reactions with nuclei is that if we see a modification of the inclusive and packed jet cross-sections, there should also be a related substructure modification. And of course, substructure is a modern way of saying jet shapes, fragmentation functions, jet charge, etc. Many observables have been investigated. Now we chose the jet charge because it's useful for flavor separation of jets. The jet charge is defined here. It's the electric charge weighted transverse momentum of the particles inside the jet to a power kappa. Kappa can vary the relative contribution between soft and hard particles, and it has to be positive for infrared safety. It was introduced a very long time ago and used for this flavor separation that I mentioned, but new interest in this observable was sparked by calculations about 10 years ago in soft collinear effective theory, which found a very simple factorization formula for the average jet charge. It's given by the kappa plus first Mellin moment of the matching coefficient on the fragmentation.
Ivan, you got 4 minutes.
Normalized, thank you, by the inclusive jet function against the inclusive jet function, and then the kappa plus first Mellin moment of the fragmentation function. We first checked that this factorization formula works well in the case of proton-proton collisions. What is shown in the figure are Atlas measurements of the jet charge for flavor separated jets, up quark jets and down quark jets for several different choices of kappa. And you see first the separation, the clear separation, and second, the good theoretical description. Now we can apply this, of course, to electron, proton and electron nucleus collisions. And in electron nucleus collisions, the factorization formulas can obtain a medium-induced component. It once again can be expressed in terms of the in-medium splitting functions that are the fundamental objects that I started with. And then there is a component from the in-medium evolution of fragmentation functions. The final results are shown in this figure. And it in fact shows two different things. The upper panel shows the nuclear modification of individual jet charges, for example, up-quark jets. The different bands are for different parameters kappa. And what you actually see is directly the medium-induced scaling violation in QCD. It would be extremely cool to actually measure it. It's not a very large effect. It's a 10% effect at most. But we can do precision measurements at the IC, and this is something to look at. Now, if we look at the average jet charge, the physics is different. A nucleus contains protons and neutrons, different combination of up and down quarks. And this is one way to look at isospin effects in nuclei and help the extraction of parton distribution functions in nuclei, specifically isospin breaking at large values of Bjarke and X. So before I conclude, I want to put this in perspective. There are other proposed electron-ion collider facilities. Now we know that DIC is almost on show and CD1 will be coming sometime soon. But there is also LHeC and also even electron-hadron collisions, possibly at FCC. And in this particular case, the center of mass energies are very, very high. So they're way too high to study this type of physics of parton energy loss and hadronization. So LHeC would be good to study nuclear PDFs and small x physics, but certainly not the physics of hadronization or energy loss in nuclear matter. There is also the electron-ion collider in China. I mean, this is a schematic, looks complicated to me, I'm not an expert. But more importantly, these are the center of mass energies that the two stages of EICC will cover. And those are, in fact, ideally suited to study hadronization and energy loss. The only thing about the electron-ion collider in China is that perhaps it will have limited reach for saturation physics. So this brings me to my conclusions. So jet physics in EP and EA is an important part of the IC program, and it can provide information about nuclear PDFs, the physics of hadronization, and the transport of energy in the nuclear environment. So to study this physics, however, we have to be smart. To study particle propagation in matter, we need lower center of mass energies and forward rapidity. That would be the proton or nucleus going rapidity. And also high luminosity would be very beneficial. So we did the first calculations of light hadron and jet production and also jet substructure in EP and EA. And we found that the nuclear modification is significant and it will be easily measurable with DIC. This is something on which you guys, if you're interested, can build experimental programs. We also proposed successful strategies to separate initial from final state effects. This will help both extraction of MPDFs and also cold nuclear matter tomography. And even the jet charge can be used for flavor separation and other more detailed studies. And so the final comment is that the EIC seems to occupy this ideal middle ground. It will allow both studies of parton energy loss and hadronization and also gluon saturation, whereas competing facilities will be optimized either for one or for the other. So thank you.
Thank you, Ivan. Very nice talk. So I think we have time for one quick question from the audience. So questions for Ivan?
Yeah, Daniel here once again. I have one question.
Go ahead.
Can you hear me?
Yes, go ahead, please.
On your previous slide, you made the comparison with LHeC, EIC, and so on and so forth. Are these effects visible at Hera, where you have proton-electron data?
So what I was looking at are electron-nucleus collisions. I was comparing electron-nucleus collisions relative to the electron-proton collisions. The data at Hera is very useful to constrain the electron-proton part, but they did not have in a collider node electron-nucleus collisions. They had what I started at the beginning, a fixed target node. They used the electron beam from Hera to collide it on fixed targets. And they did what I consider the first usable studies modification, energy loss, and hadronization in cold nuclear matter. So this is what we have from HERA. So really, we haven't had anything else in DIS in cold nuclear matter. So the EIC would be the next step. But the information that we have gotten from here is, of course, extremely useful to constrain the theories and also kind of get some preliminary handle on transport properties of cold nuclear matter. So when we predict something for our experimental colleagues, it's meaningful as opposed to just kind of wild guesses.
Okay, I see. Thank you very much.
You're welcome.
All right, thank you very much, Ivan. So
let me unshare this.
Okay, so please. So next speaker is Heikki Mäntysaari, and he will talk about electron-ion collisions at the LHeC and FCC-eh. Heikki, go ahead when you can.
Okay, thank you very much for this opportunity to present some parts of the LHeC and FCC physics program on behalf of the LHeC FCC-eh study group. So the motivation to do EA collisions in these future facilities is that we want to probe what I would call here the cold QCD phase diagram in this region of say phase space where the parton density is very large, but we also have high enough scale such that we can use weak coupling techniques to really understand what is going on here. So we all know that in QCD that we have basically gluon splitting, which results in very large parton densities at small x, which is the x-axis in this plot here. So high density small x here on the right, and then at small enough x, we have large enough density to actually enter the nonlinear regime of QCD. At the LHeC and FCC, what we have is a very large center of mass energy, so very small Bjorken x, which translates into high parton densities, especially because we can use nuclear targets where we have a huge A to 1/3 approximately enhancement for these densities. So LHeC and FCC-eh provide access to study quantum field theories, or in this case QCD, in this very nonlinear regime of the phase space. Okay, this very wide kinematical coverage is illustrated here. What is shown in this XQ² plane down here is the current nuclear DIS data. And because all this data comes from fixed target experiments, that only covers the high x small q² part. And then what can be accessed at LHeC is basically this blue region, and then the extension that one gets at the FCC is then these green these green lines here that extend the coverage by say an order of magnitude or so. And what is important here is to compare this kinematical coverage to the saturation scale. So this saturation scale characterizes the scale where the nonlinear dynamics in nuclei, in this case lead, becomes important. And you can see that basically within the LHeC coverage or FCC, we can clearly access both the region where the nonlinearity should be very large, and then as well as the dilute region, which is very important for somehow quantitative understanding of QCD dynamics in this region. Okay, of course, there is a very comprehensive physics program for these future colliders, and in this talk I can only cover a very small part of that. We also have plenty of talks in this conference. I'm focusing on some parts of the EA part of the physics program. I also want to advertise the LHeC CDR update that was put on archive last year that covers the capabilities and the physics program in much more detail. But here are some topics that I want to cover in this talk, somehow as an example of what you can do with these great facilities. Okay, so let's start from nuclear PDFs. So thanks to HERA, where we have very precise structure function data for protons, the proton structure is known very accurately down to, let's say, x10 to -4, maybe even smaller. I mean, that's the ballpark. And then at some point, the uncertainties, of course, start to increase. Now, of course, LHeC can also help with the proton PDFs, but what's more interesting is the fact that with the nuclear DIS in the collider kinematics, you have access to very small x, and then you can constrain the nuclear PDFs in the small x region where uncertainties are very large. So just an illustration, here I'm showing the data that is included in the state-of-the-art EPPS-16 nuclear PDF. You basically see the fixed target nuclear DIS data, and then some data from LHeC and RHIC that is mostly at high Q squared. So what you can measure at the LHeC, here is one illustration for the structure functions. I'm not even showing the fully inclusive structure function, but here I'm showing the charm contribution and the B quark contribution. And the different sets here are different at different Birken x's. So basically for charm, we can go down to 5 times 10 to -6 or so. For bottom, it's a little bit higher than the -4. And you see that over this wide range of kinematics, the simulated uncertainties are very small. So very precise measurements even for these charm and bottom contributions are possible. Then you can to actually observe the nuclear modification, one probably wants to look at something like cross-section ratios. So here I'm showing basically total cross-section for nuclei divided by A times the cross-section with proton. And then in the absence of nuclear effects, this ratio is 1. And this pseudo data that is shown here is generated using EPPS-16. So this is somehow the magnitude you could probably expect. And then you can see what is the projected accuracy. So this pseudo data has basically negligible uncertainties over this wide XQ squared region that is shown here. Then we can quantify the impact on nuclear PDFs. Now, to quantify that accurately, one can use the so-called EPPS-16 star nuclear PDF that's made by the EPPS collaboration, with the modification that you don't actually assume very strict functional form for the modification down to small x, but you use something more flexible than in the main nuclear PDF. With the motivation that with the flexible parameterization, then in the region where there is no data constraints, the uncertainty band basically explodes. So as it does, so this is basically what you get for the Gluon modification at the initial scale when you include all the data that goes into the EPPS-16 analysis. Then you can include the LHeC pseudo data to the fit. And in the middle panel here, what is included is the total F2. And you can see that you start to have a much better control for the Gluon modification. And what really makes a difference is when you include the charm data. So then the right-hand side panel includes the full F2 from LHeC and the charm data that I was showing on the previous slide. And you can see that the modification is very well, very accurately obtained down to say x10 to -4 or so. Okay, if you do something like in EPPS-16 or in other nuclear PDF sets, then what do you actually? So these nuclear PDF sets, you do a global analysis. You include all the work data, and that requires you to also introduce, say, A dependence and some more moving parts. If you really do a precision analysis, what also becomes possible at the LHeC, thanks to the wide, the huge amount of precise data, is that one can actually extract directly the PDFs for nuclei. And this precision is illustrated here. Let's directly jump to the middle panel here. So what is shown is the relative uncertainty of the gluon distribution for lead at this scale as a function of x. Sorry, the font is quite small, but let me point the relative numbers to you. So this red band here shows the relative uncertainty if you extract lead PDF from the LHeC data. And then this uncertainty band is less than 10% if you at say until you reach 2 × 10⁻⁵ or so. And then if you also add the FCC data, you get the black band, which is so that somehow increases your accuracy and X range by almost the order of magnitude, not quite, but almost. The lower panel here illustrates the difference to the EPPS 16 nuclear PDF. So this let's say gray band here is what you get from EPPS at this scale for the gluon modification. Note that so this panel was for the absolute gluon PDF, and the lower panel is for the gluon modification. And then you can compare this uncertainty to the projected uncertainty for the lead PDF that you can extract, and you can see the huge improvement. And this allows for a precision test for collinear factorization also with nuclear targets. Okay, let's jump to exclusive scattering, and we'll talk about especially exclusive vector meson production, in which you only produce one particle. So you have photon nucleus to say Tsai nucleus. The advantage is that you cannot transfer net color charge. So at lowest order, you have to exchange 2 gluons. So very roughly, the cross section goes like gluon density squared. In reality, it's more complicated because it's an exclusive process and PDFs are inclusive. Another advantage is that you can measure the PT of the meson, and that is the total momentum transfer, which is the Fourier conjugate to impact parameter. So there is also possibility to study spatial distribution of partons. Now, because this process is highly sensitive to nuclear modifications, you can expect to see significant differences between EP and EA collisions. And what is shown here, let's say on the left-hand side here, is the exclusive Tsai production in EP collisions and E-lead collisions as a function of center of mass energy, normalized such that in the absence of nuclear effects, these 2 curves would be the same. And you can see that there is a very clear nuclear suppression estimated based on some particular color glass condensate model calculation, which is very much stronger suppression than what you expect to see, say, for F2, especially, mainly exactly because this is so sensitive to the gluon distribution. In addition to exclusive diffraction, you can also do inclusive diffraction. So require that you produce a system with given invariant mass. So it could be a few particles or many particles. You set the invariant mass and require no net color transfer. So you have some rapidity gap in the detector. And then you can measure the total diffractive cross sections. There is some LHeC simulation on the left-hand side here. You can see that the precision is extremely good over wide range of Q squared, and beta is basically related to the mass of the system. And when you have such a total cross-section data, you can extract diffractive PDFs that have never been determined for nuclei. So this is something completely new that will be possible. And this provides a very powerful test for many models, because then it's possible to require all the models to describe nuclear effects simultaneously in both inclusive and diffractive events. Okay, for the last couple of minutes, let me say a few words about somehow genuine nonlinear QCD dynamics. Of course, say nuclear suppression in inclusive and diffractive scattering, those you can also relate to nonlinear QCD dynamics that could be, say, gluon recombination in this part of the phase space where the gluon density is very large. But then more powerful probes you have also when you look at more differential observables such as two-particle correlations, as I will shortly show. So first, let me once more emphasize why high center of mass energy and why XQ squared coverage is so powerful, because you can really study the transition from the dilute to dense region. So what I want to say is that it's not really a sharp transition from the dilute to the saturated region, but there is it's a smooth transition when I say illustrate it here by showing the nuclear modification to F2. If I start from upper right corner in the dilute region, there is no modification, and then when I move down here to small x and scales below the saturation scale of the lead, I start to see a significant nuclear effect. And then one can try to say fit the measured nuclear suppression or measured total cross sections based on BeAGLE evolved PDFs using different cuts in the XQ squared plane, and observing tensions in these fits could be clear signals of saturation effects, for example. Okay, and then I wanted to discuss this more differential observable. So dihedron production, where and azimuthal correlations that's shown here. One calculation is shown here. So basically, you have virtual photons splitting to a dipole, and these quarks are initially back to back, and then they get some kick from the target that's of the order of QS, and then this kick can wash out back-to-back correlation. Now the solid black line is the calculation for the photon-proton interaction at 2.75 TeV center of mass energy, and then when I increase the center of mass energy by factor of 2.5 or so, this gets a little bit broader because smaller x, the QS is a bit larger in the proton, but it's not such a huge effect. But what really makes a difference is the fact that we have nuclear targets, so we can replace the proton by lead, and then you see a huge suppression, or expect to see a huge suppression for this away side peak. So really, nuclei are very powerful in probing this nonlinear QCD effects. Okay, seems that I'm a little bit out of time. But I just want to flash that we can do we have a very comprehensive physics program for LHeC and FCC-eh, where we have access to nuclear DIS in the TeV range. I mentioned some parts of the EA physics program that was possible within the limited time. And then I want to highlight that there are plenty of LHeC talks also in this conference that I advertise here. So thanks for your attention.
Thank you very much, Heikki. So questions for the speaker, for Heikki? I have one. Okay, Max first. Go ahead.
Hello, everybody. Thank you, Heikki, for this wonderful talk. I wanted to emphasize that there's something which we are not really emphasizing enough, I believe, which is that we can do EP and EA parton distributions completely. So we somehow get the ups and downs, the anti-ups, the anti-downs, the valence, the heavy quarks in EP and NEA down to very, very low X. And the concept would be to find saturation in EP, and then compare it with EA and understand the nuclear modifications and test the existence of this factor and then measure it, so to say, flavor by flavor. This is really an extremely impressive program, which I think like you showed very well, but it's only the beginning you showed. We are not only having gluon and one quark type, but we have them all together. And then if you add these data to the EPS fit, then of course, since the EPS fit has to cover all data, the chi-squared is wide open, tolerance criterion is very large, And therefore, you had highly precise data, but you can't do much because you fight against these chi-squared. So the comparisons are always a bit misleading, and because these data have a completely different quality. The only problem is we don't have them yet. Thank you very much.
Thank you, Max, for the comment. Yeah, my question actually was still on the nuclear PDF. When you show the impact study, I guess it was on slide 7 or so.
Yep.
You mentioned at a certain point that you actually include the charm, and of course you have a much better constraint of the gluons at low X. But you never included also the bottom, or is it also included?
No, I don't remember the details. This is something that one would
Because
probably
at a certain point you show that the B also can be measured with precision. I think this is slide before. Yeah, here.
Yes. Yeah, but I don't know what is the impact of B data on this.
So you don't expect a significant impact because it ends at 10 to the -4? So
my guess is that charm really dominates, but I see Max has still his hand raised. I don't know, or Paul, if someone more familiar with that study can comment.
So what actually B brings in here by measuring precisely the B quark production?
It would bring something in addition, not so much, I guess. It's more the study of the B and the charm in the nuclear environment. What I really believe is that these results are a bit, as I tried to indicate, a bit misleading, because the CPPS really has everything open, has a chi-squared of 52 or something. So then you add one data after the other, they do something, but they can't change it because there's such a wide corridor, they can fit anywhere. And therefore, I think this analysis is a bit indicative, interesting, but we also know from Hera that the gluon is completely determined by the scaling violations of F2. You don't need necessarily charm. Charm is very interesting by itself. I don't think you gain so much. So this is a bit with caution to be looked at.
All right, thank you very much. And thank you, Heikki, very nice talk. Okay, so if you stop sharing now, next is Wenliang Li. She will talk about U-channel physics observables from JLab Hall C to the EAC.
Yeah. Oh, thank you very much, Salvatore. So can you see my screen?
Yes, we can.
Can you hear me? Wonderful. All right. So yeah, okay. So okay, thank you very much for attending my presentation. So I'm Wenliang Li, and within the community, people call me Bill. I'm a joint postdoc at William Mary and the Jefferson Lab EIC Center. So it's really my great pleasure to take you to a journey that looking at the U-channel observables from JLab Jefferson Lab Hall C to the EIC. So first of all, let's look at Jefferson Lab, which consists of a 2 superconducting linear accelerator with 2 bending arcs. Then we have electron injected at the injector, then raise about 5 labs getting to experimental hall A, B, and C. And we have a maximum energy of 11 GeV, then 12 GeV available at hall D. So each of the halls at Jefferson Lab is equipped with a very unique set of detectors, which will achieve their very unique objectives. We have the hall B, which is a class 12 experiment equipped with a large acceptance detectors that will be seeing multiple interactions simultaneously. We also have hall D with large acceptance detectors, but it is a real photon beam. We have a hybrid search, hybrid meson search going on there. For hall C, we have a pair of very high resolution spectrometers that aims to look at the rare interactions and to perform LT separation. So at Jefferson Lab, we have our physical observables normally quantified or defined in or described by 4 different kinematics variables. We have the Buhr-Kinex, which is just a momentum fraction available to us normally just at valence quark region, 0.2, 0.3 ish. Then we also have the Mandelstam variable S, that is or the square root of s, that's the invariant mass of the interaction. That dictates whether an interaction is in the resonancy region or not. So note that all of the interactions that talked about in this presentation is above the resonance region. So then we have the Q squared, that is the wavelength of the virtual photon probe. That's just the resolving power of our interactions. Then we have the Mandelstam variable T. That is inversely correlated with the impact parameter. So in Jefferson Lab, if you want to see deep into the proton, then we raise Q squared, we raise T, and in doing so, we reduce the impact parameter B, and then we kind of just resolving the quark-like structure within the proton through the virtual photon probe. However, notice there is something missing here because the Mandelstam variable U is completely missing from all of these kind of a grand look of the interactions. So GPD, as we know, it's mainly predominantly being studied from the forward angle observable, and it's actually required that the meson produced from the GPD is actually have to be extremely forward going to satisfy one of the two factorization conditions, one being large Q squared, the other one has to have a very small t. But then if you want to have a U-channel process, the meson and the proton that is in the picture is kind of reverse role. We're in the TDA, which I call it the backward factorization scheme, then the meson produced have to go extreme backward. As you can see that we both have a collinear factorization between the hard and the soft scattering or soft structure. The TDA have a 3 quark that hydronize forward compared to just a 2 quark interaction between the collinear factorization and GPD. So, okay. So how do we actually find such U-channel interactions? So I'm going back in time, finding a example through past experiment. First, we have the experiment in 2003, which led by Gauss-Huber, trying to look for the form factor of the charged pion. As you can see that from the EP constant timing structure, you have a very, very large pion peak over here. But beside it, there is also a proton peak, which is people initially thought, oh, this is just elastic, but somebody did a cut, did the missing mass reconstruction, and you can see that there is omega that is on the missing mass spectra. And if you're putting on these T-channel and the U-channel process side by side, in both cases, electron coming in interact with the liquid hydrogen target, electron scatters into one spectrometer at Hall C, and then in the forward pion case, and then you have a pi plus that is produced, and then this electron and pion form coincidence, and then the spectating nucleon just left behind at the target station. So this is a typical T-channel pi plus production. Where in this omega case, we have electron also come in, bounce off into one of the spectrometer, but notice that proton as a target is actually bounced forward into the other spectrometer. In this case, electron and a proton here forms the coincidence, and then omega being the lighter particle actually being left behind at the target station. So this actually requires a unique interaction picture, which is shown here, is that you really need 5 quarks to in the initial proton peak proton initial states, where you have the 3 valence quark, then absorb all of the momentum from the virtual photon probe and going forward, hadronize into a final state proton, and then we have a quark anti-quark pair that is left behind, forming this omega being left behind. So this was described by Christian Weiss and Mark Strickman as a proton being knocked out of a proton process, which is very, very interesting. So this is the analysis of my thesis. We jump right into the data. So you can see that these backward omega data show 3 points in a very, very large very large T range. This is a d sigma dt versus T plot. And then in the forward angle region, you have the forward omega electron production from class 12. As you can see that this is the first time that in the electron production interaction, a forward peak, then a plateau in the middle, and then the backward angle peak is ever seen on the same plot. And it's the same thing for both Q squared. And the community was a little bit in shock because the amplitude of this U-channel peak is very, very large. It's even 1/10 of the T-channel peak. So yes, recall that I mentioned the backward angle kinematics, the backward angle factorization scheme known as the transition distribution amplitude, TDA. So TDA actually gave two very specific qualitative predictions. One of them is that your sigma T must dominate your sigma L. And my thesis, my result has shown that even at a Q squared of 2.2, you almost have an L to T ratio of approaching 0. So it really validated the first prediction of the TDA, where the second prediction is that the transverse cross-section have to go approximately 1 over Q squared, Q to the 8 scaling behavior. And this is almost, well, this was demonstrated by the pi plus measurement from class 6. As you can see that the TDA, or the transition distribution amplitude prediction as such, describing the trend, and it almost is the same, exactly the same trend as the data for the data larger than Q squared of 2. So these evidence has given me enough courage, and so we decided to have a dedicated measurement in the backward angle region or the U-channel region to demonstrate both predictions of the transition distribution amplitude. So we have selected pi 0 as our candidate, and which is really not being seen by many of the other free data at Hall C. And we have submitted this proposal to Jefferson Lab Program Advisory Committee in 2020. We received 29 days of pack days. This is realistically 50 days of running. And the significance of this measurement is that this is really the first approved dedicated U-channel experiment at Jefferson Lab. So this is our collaboration list. Me being the spokesperson with Justin Stevens from College of William Mary and Garth Huber from University of Regina being the spokespersons. You're welcome to join us. And the experiment itself replicates what happened in the omega case in the 6GeV, where we have the electron come in, interact with the liquid hydrogen target. Electron goes one way into one spectrometer, and the proton goes the other way then into the other spectrometer, where the pi 0 is kind of just left behind. And we can use that to reconstruct using the missing-match reconstruction technique, what is the pi 0. What's the unique advantage of this pi 0 is that it's relatively clean, only with the backward angle DVCS being the only known background to this. Unlike the omega, you have the rho and etas as background. So where you have to do a lot of work to get the clean signal. So our goal is to do a LT separation at Q squared of 2, 3, 4, and 5. And then we have one additional W scaling test at the Q squared of 2, and then high Q squared scaling test of a 6.25. This is a very important bridge to the EIC program, as I will introduce a little later. So the objective number 1 of the measurement is to demonstrate that the sigma T is dominate sigma L as the TDA backward angle factorization is predicted. And we will be making this claim if the T over L ratio, you can see it's projected over here, is larger than 10 at Q squared of 5. And we will have already demonstrated the the first prediction of the TDA. And then the second objective is to look at the transverse cross-section scaling. And in fact, the experiment here is designed to have enough resolution to determine the n factor, which is q squared to the power of n. This n factor is between 3.75 and 4.25. And you can see here is the synergy of various of pi0 measurement at a W of 3.1 or S of 10, various of data that from Panda, from BlueX, from approved Hall C experiment and a future EIC, where together we'll be completing a complete Q-square evolution, including the real photon point of the small Q-square scaling, large Q-square scaling, and the real photon point measurement. And I was very happy to report that I led the effort of developing a feasibility study of looking at this pi0 events at EIC, and it was published as a part of the yellow report. So the future EIC project, you probably heard a lot about already. So yeah, so it was a CD0 approved, and the physics will be available at 2031. And the first interaction hopefully will be at IRA. Yes, the U-channel measurement looks like this. We have this is a U-channel pi0 production. Yeah, so we have the 100 GeV proton coming in, and we have a 5 GeV electron coming in like this, and then we have a pi0 produced really in the same momentum of the incoming or incident proton and go forward, and that will reach the 0-degree colorimeter, and the electron will bounce into the electron colorimeter or electron end cap, and the proton will go rather forward and close to the beam pipe. So I have done some preliminary studies to looking at the acceptance. As you can see that for the pi0, it will be, there is a good chance that depending on the momentum here, I'm showing that the 50 GeV pi0 events that will actually have a 2 photon that projected themselves onto the ZBC, considering the realistic acceptance of 4.5 milliradians, and you have a kind of shape like this. And then that corresponds to 30 to 40% of the chance of this pi0 decaying to 2 photon, where 2 photon will be simultaneously detected by the 0-degree colorimeter. But we're in the forward proton case, you can see that currently we actually have a hole in the ENM colorimeter where this proton will miss the ENM colorimeter in the hadron end cap. So it's ongoing research how to patch up this hole to pick up this proton going forward. So I also look at the complementary between the EIC and the future EICC, where it's very interesting that the EIC, thanks to its high proton incident momentum, then it's very good at tapping at for a given meson production interactions, looking at the cross section at a T min or T max, and also that looking at in the mid range, mid T range, where the EICC because of its lower incident proton momentum, it's really have a rather large coverage in the entire T distribution compared to that of the EIC. So if designed carefully side by side, I think we could really minimize the effect of this dead zone. And also I want to mention that the EICC have a very interesting possibility of looking at angular dependence at a rather large T range. And thank you very much for coming to this talk. And this is the end of it. Thank you.
Thank you very much, Bill. Very nice job. So questions for Bill? No one? So I have a quick question. Since I followed up your your work at the Yellow report. So, and you always mentioned that you have this hole in the acceptance in the forward proton.
Yeah.
Are you actually addressing now this, for example, for the IP8, if you join the collaboration, or what is the progress on this?
Yeah, I'm glad you asked that question. So you can see, Salvatore, is that I'm placing this detector is not there. You see, is the yellow blue block here. So my intention here is to use a secondary, just a virtual detector to help me to understand how much of this hole that is being patched up. So I'm currently initiating the study, and then later on, once I have a more concrete results, I will be like communicating with, let's say, experts like Julia or Alex, Jench, on how exactly, whether it's possible to patch it up and how much. Yeah. So yeah, it's under investigated.
Thank you very much. It could be nice to know in the end. Uta?
Yeah, thank you. This is quite interesting. So you mentioned as a motivation that it may give new insights in hadronization processes. Did I get it right?
Yes.
But you also mentioned that Christian Weiss, he said we are knocking out a proton out of a proton, which looks more, let's say, mechanistically. We are knocking, yeah. This, so from this graph, this hadronization, it's not really clear for me how you then model this, for instance, for the EIC study and for your future studies. So how is this linked? Yeah, this knocking out versus really there is some action from quarks and gluons with hadronize. Yeah.
So I'm very glad for your question. So here, give me a chance to look at this plot here. So I'm sorry that I didn't have time to elaborate this. So this table has shown that in terms of the DVMP and the DVCS, what is actually available at a large scale that is at Jefferson Lab also, and also the EIC. So the hadronization that you mentioned in the yellow report, they're really referring to that one cannot just look at one process and say, yes, that helps with the hadronization. No, in fact, we have found the U-channel peak for all of these interactions without exception. So I will show you even the phi, which is very interesting. So we really have to have a systematic program to tap into all of these interactions in the U-channel kinematics, which we have never done. And this is really the first, I'm presenting my study as an example for the future programs that you may have some very smart people that decide to do, let's say, U-channel pi plus or U-channel K0. But overall, we must look at this as a systematic program, put all of these U-channel peaks together, like the same way that we did for the forward angle case, where we have the GPD that kind of describe all of the link everything together. So that's where this TDA framework is about, which you have all of the meson productions together and looking at everything systematically. And just to show you a very interesting example, you can see here, this is a free data from Hall C that is not a dedicated study, and you can already see a little bit of the phi peak. I don't know what this means. And if you put that into the Christian Weiss's proton knocked out of a proton process, as I have shown in here, and you replace this QQ bar with SS bar, and I really don't understand what that means. And it's the theory that colleague have to tell me.
Okay, so, thank you, but this helped. This makes more sound.
Thank you. Thank you. And I also want to say that the phi backward angle phi production got my theory colleague most interested.
All right. Thank you,
Thank you.
very much, Bill. I think we had to move on, but you can continue offline with it, of course.
Of course.
It's
Thank you.
very nice and very interesting topic.
Thank you.
So next and last speaker, but not least, of course, of our session today is Zhoudunming 2, community called him Kong. He will talk about short-range correlation in light nuclei and light ions using the BeAGLE generator. Kong, are you online? You can share your screen.
Oh, that's right. I share myself, but
you can share yourself.
yeah, sorry. Can you see my screen?
We can. Thanks.
Okay. Well, thank you. Well, particularly, thank you for the organizers and especially the session chair, Salvatore, Daniel, and Marcus. So today, this is about a study for the EIC that is related to the diffractive Tsai of light nucleus like deuterons. So a little bit of the introductions. I won't go into details, but it's just one slide that we're interested in general in nuclear physics, the nuclear structures in nucleus that has been puzzles, where that if you're looking at this wide range of kinematics, that we have a general tool that we do DIS as the name of this conference, that we do this cross-section measurements and we compare that the process on the nucleus versus the free nucleons. And then we do some scaling and then we say the ratios to find out what's the nuclear effect. And looking at this very large range of kinematics from very small x to even very large x, they have very different physics, of course. And on the very large x, the spectrum, that we have so-called a short-range correlation, where the x above 1, I mean, traditionally, I mean, this is bounded by 1, but in nucleus, if you define it in a way that, that the x sphere can goes up to 1, above 1, and then here is the region where they observe a plateau in these ratios. And this is, they believe, is caused by the short-range correlation where you have high momentum nucleon pairs sitting in the nucleus. And then, of course, the central question is, by looking at this wide range of kinematics, why nucleus is not a collection of free nucleons. There are much more rich physics in the nucleus. And then one thing to point out is kind of interesting. You can see all this above and below 1, but it's never almost to be 1. So a little bit of the history is coming from the EMC puzzles, where almost 40 years ago that we saw the nuclear structure was suppressed from the EMC collaborations. And this is the region, so-called the EMC region from 0.3 to 0.7 in the X period. And then in recent data, there are strong indications that the EMC effect might be related to this so-called short-range correlations, where this very high momentum pair of nucleons, where this nucleon are significantly off shell, that could be the cause of the EMC effect, that they actually change or modify the platonic structures of the nucleons. And they found an amazing correlation between how much this EMC effect versus how strong the short-range correlation is. Of course, this is not a proof yet, but at least we have a very significant data in evidence to show that this might be the case. So what I'm interested is in the gluon region, where we're looking at the low X region, which is a natural question to ask, that if this SRC, the short-range correlation pairs, might have an effect, or might be even the cause of the EMC of the valence quarks, but what about the gluon structures? So more specifically, we ask, for example, what is the gluon density with or without a SRC pair? And this is just a complete analogy to the EMC effect and their correlation with the short-range correlations. And of course, if you want to take one step further, you can ask what will be the gluon spatial distributions, GPDs, and all kinds of structure questions given the context of short-range correlation pair. So one way, a very powerful tool, is to look at diffractive production, and specifically the diffractive vector mesons such as Tsai productions. And this was studied extensively at HERA. For example, I'm showing you H1 data that you see the EP collider, the highest energy collider, will produce a diffractive Tsai, and we measure this momentum transfer distributions, which is called the T distributions. And then this will be directly connected to the source distribution, which is in this case the gluon in the spatial space. So from the momentum space to the spatial space of the source distributions. And then here is the idea that we came up that for the EIC, which is to use a light nuclei that we have an electron-deuteron scattering, also using the same channel as the diffractive Tsai productions. And then we want to use it to probe the gluonic structures with the experimental control of the spectator. So the idea is we have an electron-deuteron scattering producing a Tsai, where the Tsai is, we call it incoherent productions, where the Tsai is scattered off the individual nucleon, and we're leaving the other nucleon, because in a very simple system of deuteron, the other nucleon untouched, which is a spectator. So the advantages of this new measurement is, first of all, the incoherent Tsai production directly probes the bounded nucleons. So this is comparing to, for example, more inclusive type of measurements that you just scatter off your target, but you have to really do a lot of averaging of different configurations of your target. And then the second advantage is by tagging the spectator that we can have a very nice control of these configurations, namely between, based on this EMC SRC model, that we can fine tune the configuration between a nuclear effect or without a nuclear effect. Or in other words, we can, if we tag the spectator, we can choose the kinematics in such a way that either we can look at deeply bound nucleons or even just free nucleons. And actually, there's a similar technique is being used for free nucleon structure function measurements. For example, the free neutron structure function measurements. That is very interesting, given a talk by Alex Jensch tomorrow, I think Thursday. And how do we study this for the EIC? First of all, we used the next generation general purpose Monte Carlo program called BeAGLE. This is developed mostly from Brookhaven. And then this model, simply speaking, is a hybrid model where we have lepton or electron nucleon collision, and then we embed it into an A nucleus. So we have nuclear PDFs, for example, and then we use DPM jets for nuclear geometry. So you kind of like a Glauber model to pick which nucleons and geometry in the nucleus. And then the hard scattering is simulated by the Pythia, the EP or EN process, and where the nuclear remnants will be simulated by Fluka. And in this case, in Deuteron, actually the simulation is much simpler. We use Deuteron wave functions with light from kinematics, and then we assume this PWIA, this plane wave impulse approximations. So it's much a simpler version of our BeAGLE model. We just have to use the wave functions. So this is, of course, for the EIC. I think there's no need to introduce that we'll have a very powerful machine. I just want to emphasize the diffractive and exclusive reactions are one of the major physics focus at the EIC. So this is the result. Now we have 18 GeV electrons scattering off 110 GeV deuteron, having this so-called incoherent Tsai productions. And this is plotting the total 3 momentum of the spectator and in the ion rest frame. So this is going from 0 to 1 GeV. So it's a very high momentum in the deuteron rest frame. And we usually characterize this distribution by two important regions. One is so-called the reference region. That is where in a relatively low momentum, where most of the cross-section will be on this reference region. But then the other region, we call it the SRC, the short range correlation region, is where this nucleon is in a significant high momentum. So at the tail of these distributions, and this is the region of interest of this study. And the idea is that many physics observables can be used in this way and compare the different regions and see what's the differences. And here that we have a very nice and novel simulations coming out from the yellow report, and also for the EIC IR regions. It's a really complicated region, so I'm not going into details, but the idea is that we simulate not only the detector, like for example, the ZDC, the proton spectrometers, but also the beam related effects. So we trying to come up with all the effects that can be affecting this measurement, and we simulate that with our best knowledge. For example, here, this is a process that we have a leading proton and you have a neutron spectator. So you use the ZDCs to capture your neutron. And then we can do it the other way around. We can tag a proton by using these three different protons detectors. And then it will be a leading neutrons. So just a little bit difference here that you can see the difference in these full simulations versus truth, that you can tell the intrinsic difference between different detectors and their sensitivity of this reconstructing the momentum distributions of the spectator. So details will be in the yellow report, and I'm sure you guys are aware. And a little bit more physics, which is the T distributions, as I talked about earlier. And this is the diagram I was pointing to. So one idea that coming out of this study was that we want to measure the T distributions, and there are many ways. So based on Hera measurements, that you can detect the scatter protons, for example. But if you think about in the nucleus case, and this is not applicable directly because we have some Fermi motion, and in this case, in the short range correlation, we have a very high momentum of the initial proton. By detecting the final state proton will not tell you anything about this T. So the idea is that we can use this very specific constructions of the final states that we know everything, so-called the double tagging. We tag both of these nucleons. So I can use the spectator to derive what will be the initial momentum of the initial state of this active nucleon. And then we can use both these kinematics to come up with the T distributions. So here on the left is just a indication of the method that we're using of this double tagging that we can reconstruct the T distributions. So with the leading proton and neutron spectator, you see that the T distribution is like exponentials on the individual nucleon. And then we see a very small dip here, which is coming from the septons and all the detector effect. But overall, I think this is amazing reconstruction of this T distribution. One thing I want to point out is this is just coming from a Pythia simulation because BeAGLE is a hybrid model. So don't take this absolute prediction too seriously for incoherent productions. But this is a case to show people we can actually do this experimentally. And then of course, we can add a little bit more physics in there, where by using these T distributions at the EIC, we can do, for example, Fourier transformations to get the the gluon distribution in the impact parameter space. And then with the SRC, we could have encounter a larger proton or the smaller proton, or have some deviations from a free protons. Here we using a caveat that this is as exponential, so by construction this will looks like a Gaussian. And here we take some ratios, and the idea is to see what's the luminosity requirement in this setup, that we can have some meaningful results comparing to the free proton, which is not, I would say, a day one measurement, but then it's also feasible within 10 or 30 inverse femtobarn. Okay, so here it brings to my summary. So we are coming up with a new idea with these incoherent diffractive Tsai productions in electron-deuteron scattering. And then we specifically looking at incoherent, because for the coherent case, that's a different studies, which is also very interesting. And then the physics goal, again, is trying to probe the gluonic structures and trying to study the nuclear modifications for gluons. And then again, the advantage is we can use the spectator to precisely control the configuration of the initial state. And then at the end, we also have the electron-ion collider, a simulation of the detectors and also the IR region, which is a very complex. And then we show that this is a very good physics case for the EIC, and it is definitely feasible. And with that, I stop here. Thank you.
Thank you very much, Kong. Any question from the audience? Ivan, please go ahead.
Yeah, I have a question. Thanks for the nice talk. I wanted to understand better the idea behind your proposal and also going back to the motivation. I've seen this correlation between, short-range correlations and the slope of the EMC effect for a very long time now, but I don't know if someone actually, and it is suggestive, as you said, but it's not a proof. Has anyone, in fact, incorporated any of those nuclear structure calculations in a real DIS calculation to, in fact, show that this leads to a reduction, or kind of to a smaller F2, smaller structure?
Yeah. I mean, there is proposed experiment.
The suggestive correlation versus an actual calculation.
I think there is a lot of ongoing effort, that's for sure, and not even just the theory calculations, but also experimental proof to show these correlations. And I think by using these ideas of tagging the spectators, they can specifically use this tag DIS and this different PMIS or different momentum regions, and to compare this F2, for example. And then they can directly prove this is indeed correlated with the short-range correlation. So far, these correlations are coming from independent measurement, for example, and then you plot it and found a correlation. But I think more experimental proof is needed that you can use like a light ion, like deuteron or helium-3, to further show that.
So is there any already existing data that you can point to? And I was also asking about the theoretical calculation. If those correlations are the origin, someone should take, such a model of a nucleus, do a DIS calculation, and show it works.
Yeah, I believe there is
30% suppression in the MC region.
Yeah, I believe there is some framework. I can probably point it to you offline or something. But I really think that there is tons of theoretical efforts going in this direction.
Okay, thanks. It would be useful to see it.
All right, thank you very much. Any other question for Kong? I actually have a comment. If you go to the slide 27, 26, this one. So you show this very nice reconstruction of T, and you point that there is this dip in the acceptance, but actually in the real world, you could correct for the acceptance there, right? So you can still reconstruct the T. It's that you have maybe less statistical precision in that region, right?
Right, exactly. The idea of our study, for example, the simulations and everything, we're not doing the correction like an experiment, because there's no point of doing that at the moment. But the point is to show that is experimental feasible, and also the correction factors or the acceptance corrections, things like that are under control and small, so that it will induce less uncertainties. And then this is definitely can be corrected.
All right, thank you very much. And I think this brings us to the end today. So I would thank all the speakers today that participated. It was a very intensive, very nice sessions to me. And see you tomorrow, guys. Thank you very much.
Thank you.
Bye-bye.
Thank you all. Bye-bye.
Thanks.